just before we start this video, I just wanted to address 2 points. One, if you're from YouTube, since this is the last part in the series, well, the last part in actually making the computer, the download link will be in the description because it's finished. This will be the download world. I've put it in a a void world, just to make it easier. And the computer is finished, and the program it comes loaded up is the Fibonacci sequence. So yeah, feel free to try it out. If there's something wrong with your computer, try and compare this computer with your computer, see if you did anything wrong. But yeah, and then for people from MCPEDL, there are 2 things you can do with this computer. You can either just have a go, test it out, see how it works really, or actually try and program it, which is a bit harder. But if you watch this whole video, sadly yes, you might have to watch the whole video to understand how to program it properly. You'll probably be able to program it with other, just different stuff. It'll be very hard, but you should, even though this is quite a simple computer, it still will be quite hard to program. So I advise, if you are going to try and program this, so maybe to do something else than the Fibonacci sequence, then definitely watch the entire video. So for people just wanting to try this out, basically the program loaded onto it is the Fibonacci sequence. So if we go, this is basically the program it does. So it goes 0, 1, 1, 2, 3, 5, 8, 13, and then the rest of these are missed out because it's only a 4-bit computer, and these are more than 4-bit numbers, so it'll just stop working after that. But the way you actually run this computer, by the way, this actually does calculate it and doesn't display it. If you watch the whole video, you'll see how I programmed it, so it does calculate it. But it's quite simple actually. It basically, I can't really find it here, but it basically adds the previous number, both 2 previous numbers, and then that's the newest number, and it does it again and again. So for people here wanting just to try this out, the way you're going to have to turn this computer on, you don't just flick the on switch. What you're going to do is you're going to have to reset the computer first. What you do, you click clock once, and then these 3 buttons in any order, it really doesn't matter. And then once you've done that, you can start the computer. To start the computer, just turn it on like that, and it should turn on. That light might not always turn on, it just, for this program it will. And it would have executed line 0, that's why that light did turn on. Then, to actually start the computer up properly, you're going to have to turn the clock on, and then it should start up. And as you can see, it's already done 0. Now it should do 1 next, as you can see, and then it should do 1 again. You won't really see a change in that. I think it already has. Now it's done 2, it should go to 3. 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 5 is 13. And then it would be 21, but since it overflows, which you can tell by this light coming on, then it won't work. So, but yeah, that's pretty much how to try it out. It's not an amazing map, but I basically just published this onto MCPEL just for the people who actually will know what this computer is and know how to actually use it properly. For the most people will probably just think it's pretty cool, and yeah, it is pretty cool. But for the people who actually know how the computer really works, then I hope this interests you, and I hope you can actually learn something off of it. So yeah, well, I guess it's time to start the video now, so yeah, let's get going. Hello, the Darkness344 here. Well, our computer is pretty much done now, so I've decided let's finish it this episode. So this episode I'm going through, there's only one more physical thing we need to build on the computer, and then all the rest of the episode can just be purely programming and also advice on what you can do. I may upload 1 or 2 more videos on this, but just showing how you can upgrade it and stuff, but I think I probably can cover most of your questions and stuff you might have in this video. So the first thing we're actually going to do is add another user interface function, and as you can see, I've already planned out where it's going to go. It's going to be clear ALU. It will basically clear the ALU registers, as you can see, because if you have something like this might be annoying. And of course, in certain programs, if you want to skip out a few lines in your program, you're going to have to clear your ALU registers first and stuff. Just like the Fibonacci program that we're using, the first line of code always says clear ALUB, basically. And so, yeah, what I've done is I've programmed the Fibonacci sequence in, and we'll go through it and I'll show you step by step and we'll program it and stuff just to try it out. And this computer works, it's pretty cool. And so it does work, and it's faster than my previous one, and as you can see, this is the maximum clock speed. First of all, I'll just show you what it can do. So basically, to reset it, we're just going to hit all these buttons, and then we'll clock it once while it's off, and then that should have reset it. Now to turn it on, you just turn it on, and it should turn on and immediately execute line 0 as soon as you turn it on. Then we can turn the clock on, and as you can see, I've set it really slow, and the Fibonacci sequence should go 0, 1, 1, 2, 3, 5, 8, 13, etc. So as you can see, it's going pretty fast. So it's done the 2 1s, now the 2, now the 3, now it should do the 5, now it should go to 8, then to 13, and then I think it overflows and it goes back to 5. So that means it's basically overflowed, and yeah, it's gone over 4 bits. So that's why it goes on those weird numbers. And if you want it to keep on going, all you had to do is just increase your AO. You increase the computer size. So instead of it being a 4-bit computer, you could make it into an 8-bit computer like the one over there. And I think 8-bit computers are pretty much what you want to be aiming for if you want to get into this computing thing, Redstone engineering, because they're very useful to use, 8-bit computers. Whereas like a 16-bit computer is great because it's a lot more powerful, but it might actually be a bit too big sometimes. And if it does take a very long time to build stuff, so if you want to keep it compact, you can build an 8-bit computer like this one. This one uses an old ALU, but this is pretty much the size of an 8-bit computer, a very simple one. This is very simple. It has 8 lines of code, 3 bytes of RAM, very simple ALU that can do most functions. That's very slow and a bad design, and even conditional branching on it, which is very simple to add in. It's the very simple conditional branching, so it'll branch if the ALU outputs 0, which of course is broken on this one. I did mention it. I'm not even sure if I have a program on this. I haven't programmed this one yet, to be honest. I just build them. But yes, so we're going to be basically programming this computer this time. So first of all, we're going to be putting the reset ALU. So what we're going to want to do is we're going to have to move this switch, aren't we? So we're going to move it over to here, and this is going to be the on/off, and we'll have it on the same lever. Of course, we'll want a lamp, and that will be our new switch. And we can just bring this over like this. And this is because we're going to add a new button. We don't need anything here, so I'm just going to fill that up. And we're going to add a new button, and this will be reset ALU registers. And all that will do when you click the button, because it's going to be a button, not a lever. When you click the button, it'll just, I don't know why that didn't go into my hotbar. When you click the button, it'll just reset the ALU registers. You can lay the buttons out differently if you want, as long as it reaches. So now what we're going to do, to reset the registers, all we have to do is fire a command into here. But what that will do, it'll update the registers to whatever is on the main data line. We want to reset it to 0. So what we're going to have to do is send the number 0 down the main data line and then update it. How are we going to do that? Well, what we're going to do is going to do the same thing as we did with the RAM. By anything on the main data line is going to just be cut, and then it'll just leave the number 0. So if we don't want to add more timing to this, we can just use pistons instead of adding extra repeaters. We can just use this very simple technique by going down one like this, and then across like this. And this will not extend the redstone signal length any longer at all. However, it means if we put a block here, it stops. So what we can do now is go up with our sticky pistons, and we can, I've gone too low. If we go up here, we can place a piston, and when it's off, it should be like this. But when you turn it on, it will block that off. So let's just try it out. If we send a signal down this line, as you can see, it's going into the ALU registers. But when you turn it off, it stops and it blocks it. And this will basically be how we're going to reset the thing. So of course we're going to need to go across all of these and put in sticky pistons for all of them. There we go. And these will have blocks on them. Then if we go like this, we should be able to power all of them. The levers on the piston, it has to be here. As you can see, like that. And then what we're going to want to do next is, as soon as we power that, we want to then update the ALU registers. And the way we're going to do that is by sending a signal into this. So we don't have much space on the top here, but we can always send it from the bottom. So either what we're going to do is put some torches here or put some torches under here, but this one's the easier way. So if we put one torch here, it'll turn on, but we're going to have this as a NOT gate. And if we put another torch there, it'll turn off. So whenever we trigger this torch, it'll send a pulse down, updating the registers. And we're going to do this to the one over here as well. Whoops, the block does not appear. Very simple, just like that. And then we're going to want to be able to join these together. So we're going to go like this with the redstone, just like that. And so whenever we trigger this, it will trigger both of them, as you can see. That wasn't a very good example. There we go. It triggers both of them when you click that. Now we're going to actually need to do some timings. So whenever you click this button, it puts this piston down, and then it triggers this. And this piston has to be down for a certain amount of time, so we're going to have another pulse lengthener. So let's just get some comparators real quick. And I know we probably don't need this, but it's probably for the better just in case. So if we go over like this, and we're just going to replace this button with a lever for now so we can see the signal length. And about here, we're going to put a repeater here. And comparator, comparator. Pretty simple, and this should be a very simple pulse lengthener. So as you can see, when we click this button, it goes down, waits a bit, and then pulls it up. As you can see, it did that weird thing where it pulled them up one by one. If you don't want that, you can just put a repeater here, and this block should still be powering that piston. So let's try it again. There we go. So let's try it from here. They should all be pulled up at the same time. Perfect. Bit of game lag there though. So when we click that, they'll all be done at the exact same time. Much simpler. Now, the next thing we need to do is actually power these, don't we? So what we're going to do is pull from this. We're going to go not much space here, but I guess we can do it from this side. We're just going to come down like this and make a staircase all the way down to that level. Let's try and make sure it's on the same level. Perfect. Whoops. Now we'll just bring this all the way into this one, and then we should just be able to hook it up like this. Just like that, and there we go. We'll of course need repeaters, so what I'm going to do real quick is place a lever like that, and then find where it needs repeaters. So it needs a repeater here, and I think that's it. Well, what we'll also need to do is make sure these pistons go down before these trigger. So the way we're going to do that is we're going to count the ticks. So 1, 2, 3. 3 ticks and then we're going to add 1 on. Actually, and the pistons is 4 ticks, so we might need... actually, those repeaters will count as 2 ticks. So basically, just put this repeater on 4 ticks. That should be definitely adequate. So what we're going to do is we're going to put some... We're going to emulate this real quick by bringing some levers down and just placing them on these 4 lines, the main data lines. And as you can see, it's going in. And while we're at it, we're just going to update these registers as well by triggering these. So we can put a button here because there's a repeater here, meaning it will only trigger these registers and not the pistons. So when you go like that, it should save what we had on the data line to both registers. I'm just going to break that as well. So now we have data coming in still, and we want to reset that to 0. This is a great test because not only will it reset it to 0, there's also data coming in, and it should be able to block the data off, then reset it to 0. And if we've done it wrong, it will just be a matter of timings. As you can see, it works. Great. I hoped that it would work. Okay, makes life a lot easier. Now, we've pretty much done the entire computer, and I've tested out most of it. The only thing I haven't tested is all the RAM cells, like addressing them all, and also the subtract feature. But we can do that as I actually explain the instructions there, because this is the very important bit. There's no point making this entire computer if you don't know how to program it, is there? So, I better start explaining this sort of architecture, my sort of style of programming. So basically, let's just explain how the computer works. So data from the main data bus, so this is the program counter. This is basically where you input the code, and I mean this is the program counter over here. I can't even find it. Yeah, this is the program counter, and this is where you put your code in. And each time the program counter, each time a cycle of the clock goes, the program counter goes to the line addressed. This is very clever because it means it won't just go to the next line, it'll go to the line addressed. Because if you had something like this, I'm just going to show you a very simple counter, binary counter. This would be your average program counter, and then you'd have another block, and the same thing over here. And believe it or not, my very first YouTube was on, my very first YouTube video was actually on this, and I'm not sure what I called it like a binary counter or something, and it was on a different channel. But what we do is, this is a simple program counter. It starts off at 0, 0, when you click it, 0, 1, 1, 0, 1, 1, and then back to 0, 0. This is a good program counter because it's very simple to build. However, if you wanted to, from line 1 and you wanted to jump straight to line 3, this is a bad design. So our program counter is vastly superior, of course, and it means you can address any line. And this is very useful because in the future, if you take this computer to the next level and start learning conditional branching, which is a very clever way of using if statements. So if my number equals 5, then jump to this line. If it doesn't, then continue on with the program. That's basically what you can do with conditional branching, and you can do many other things. It's very clever. But this is a very useful program counter because you can do loops in it. So you can loop, and that's how we're going to be doing the Fibonacci sequence. So that's basically the program counter, and these lines are the lines where your program goes on. So line 0, 1, 2, all the way up to line 15. So there's 16 lines in total, but we're going from line 0 because that's easier to do. And so it's a 4-bit number that we can address it. So if I wanted to go straight from line 0 to line 15, I could, just by addressing 15 on line 0. And on the next clock, it'll jump from that line to that line. So these 4 lines, so 1, 2, 4, and 8 are your program counter. So the way it works is you basically put the number on you want. If you put the same number as the line, so if I left this blank, because this is line 0, it will stay on this line forever. It will not change. The way you do loops is, so here's a simple loop. It goes from, go from line 0, go on to line 1. From line 1, go to line 2. From line 2, go to line 3. From line 3, go to line 4. From line 4, go to line 5, which is this line. From line 5, go back to line 2, which is this line. And then these will keep looping. And notice how this isn't included in the loop. That's because this executed once, but isn't included in the loop. So you could have 1, 2, 3 lines that just execute once, and then your next amount of lines can keep looping and do the program over and over again. And if you have conditional branching, you can do them over and over again till you get a certain number. Very clever. Now, I was also working on some like a programmable conditional branching, so you can program the number you want to jump on. And there was either two ways of doing it. I either program it in RAM or ROM, so you can actually set the number with the computer. I'll have a look into that because that could be very clever. Also, if there's any more tutorials you want me to do, feel free to leave some comments, because it could be really cool showing off some other stuff as tutorials, so you can learn how to do stuff like that. So that's your basic simple stuff, your actual program counter. Yeah. Now these next 4 lines, it goes 8, 4, 2 and 1. That's because it's actually this way. The thing with binary is you can either go from left to right or right to left. It doesn't matter. It's still this 0, 1 and 1, 0 could technically be the same value, but they're just going left to right and the other one's going right to left, if that makes sense. But as you can see, our main data line is going from the left to the right. So the least significant figure is on the left and most significant is on the right. So it goes 1, 2, 4 and 8. And this is because it's a 4-bit computer. You only have 4 values that you can put in, and it's either a 1 or a 0, which would be blank. And the way binary, you can address up to 15 different things. Well, actually 16 if you include 0, 0, 0, 0, because these represent places. So if I wanted to put in the number 9, not line, it would be the number 8 as well as the number 1, and that would be the number 9. So yeah, that's that basically. And this is the main data bus. This is where you send data into the computer, and I'll show you that right now actually. And also the main data bus on this computer, data actually can come from stuff into it through the program counter. Most computers, it would skip the program counter, but the way I just laid this out is it can come through the program counter. It doesn't have to, it can come straight into these ones, but it just made it much more compact, more small. So let's show you the main bus. This is the way the data flows. So these are your 4 things. I should have made these out of a different color. So they basically come all the way up to here. So this one, this one, this one, and this one. And they flow all the way round here into the ALU registers. Notice they go into both register A and register B. This is because you only toggle one register if you want. So when you say I want to load whatever is on the main data bus, that would be these values. Let's just break this real quick because this is quite annoying. If I wanted to say load whatever's the main data bus into ALUA, I would just do that with the command, where is it? ALUA here, or ALUB. And so I could just trigger that command on the same line as the number that I put in, or the number that I get out from RAM or something, and it'll come from the main data bus and it'll go into the value and it'll trigger the latch, and it will put whatever's on the data bus into the latch or the register. And yes, you can technically do both at the same time, it will work. So say you wanted to add, if you wanted to do 5 times 2, you could just do 5 plus 5, because that's technically 5 times 2. And you can do that on just using one line to input to both registers. You wouldn't have to input the number 5 to register A, then input the number 5 to register B. You could do it on the same line if you really wanted to, because they're independent of each other, so it doesn't matter. Then we have the register commands. I just explained that. Then the main data bus can either go into the, well, it goes into the ALU and it also goes into the RAM, as you can see. And basically what happens, it travels through here, goes into the RAM, and it goes into all these RAM cells. However, these RAM cells only save or update, because they're registers, they only update if you specify the RAM cell you want to update, and you also say, I want to update it, or save data to it, or write to it. And then reading is pretty much the same process. Whenever you just specify the RAM cell you want to read to, it will read from that RAM cell and read it onto the main data bus. So it'll read the number from the RAM cell and put it onto the main data bus, where you can input it to a register, or, I don't know, display it if you wanted to. So that is how the RAM works. The RAM saves stuff. Then the ALU. So this ALU is quite upgradable. The only operations it can do is add and subtract. And you can't really do that much with them, but it's still clever. It would have been better if you had like add, not an and, but this will still work fine. It's great for a basis computer. I will also show you a better ALU that you could use, but that will be more complicated. So you can either, with this ALU, it will do the operation, both operations at once, because this has technically two ALUs. It has an adding ALU over here and a subtracting ALU, and both the answers will come down into this line. However, they will only output whenever you say output. So if we go over here, you say the display command basically just updates the display to whatever numbers on the main data bus. That should explain that. Then we have the add and subtract command. Whenever you say the add command, it will basically give the output of the ALU. So basically whatever these registers contain, it will add, it would have already added them together. Basically this ALU basically adds the contents of the registers as soon as you put the contents inside the registers, and then it will only output when you say the command add. So when I want to add the number, it will lift these pistons, and the command would come through. 0 plus 0, because there's zeros on the register, is 0, as you can see. If I did a different number, say I'm going to have to input some number, so I'm going to do 1 plus 1. Let's just update both registers so it's 1 plus 1. As you can see, you can update both of us once. I need to find that lever and break it. So ALU A, ALU B, the registers. So it goes A, B, A, B, A, B, A, and B. Because A goes into one part and B goes into the other part, because you put two numbers in. So 1 plus 1, as you can see, is 2. And there's no output, but whenever we give an output, it will give an output. However, if we want to subtract, we can do the exact same thing. Whenever we give an output, it'll give the output. And of course, 1 minus 1 is 0, so the output will be 0. So that's the ALU. The display I covered in the last episode, so you should be very familiar with that. Basically, it takes whatever's on the main data bus, displays it to this all the time, and also, whenever you say the display command, it updates these registers to whatever's on the main data bus. And this is the decoder, and it basically decodes binary to base 10, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. So I don't even know what to call it. That's kind of sad. I don't know but it basically decodes it and displays it. So this is the display drive, because this drives the display, and this is the actual display. This is a 7-segment display. These are two separate things, do not get them confused. The display just displays whatever is put into it. The display drive drives the display. So say I wanted to put the number 7 into it, I would have to turn on certain pixels on that. The way I do that is, instead of having to turn on this pixel, and this pixel, I can just have a decoder over here saying whenever I put in the number 7, turn on those 3 pixels, and it will turn them on. And that's what the driver does. You can use this basic concept is used for every display driver. Say you had a GPU and you wanted to draw a square on the GPU, you just put like a binary equivalent of a square in, and it would decode it and put out a square. So say like a specific binary number says, oh, draw a square, and you put that number in, it would draw a square. Very simple. Then I think I've explained pretty much every single bit. The only thing I haven't explained is the UI. This is the user interface. Basically, it just allows the user to do stuff with the computer. Note that there is no actual input panel. That is because, personally, I don't really like input panels, and I like I don't really like the interactive side of computing. I like the raw power of the computing. So that's why none of my computers would have like a keyboard or like a mouse pointer or an actual nice text engine. I mean, it's a great idea and it would look really good, and you get a whole lot more views out of it. However, I like just using the actual coding because I find that more interesting for myself. Basically, your user interface has an update display command. The actual program has that too, but you can do it from the user interface. It updates it to 0. Actually, no, it updates it to whatever's on the display line. So if you wanted to, you could, halfway through your program, you could just click that button and it'll display it. Then you have clear all RAM, which basically sends a command to the RAM and clears every single cell to 0. You have your clock on and off. This turns the clock on or off. You have these 3 repeaters here, which you can adjust the clock over here, but then I mean you can adjust these ones too if you really wanted to, but these ones are nice on the go kind of things. You have your newly installed reset ALU registers, which basically resets the ALU registers to 0. So if we click that, as you can see, so if your ALU's ever flickering or something, just because of your program was too slow for your clock speed, you would have to adjust your clock speed, and your registers flicker, you can just hit that button. Then you have your on-off switch. This basically turns the program counter on-off. When it's off, every single line is going to be off. None of them, not even line 0 would be off. All of them are off. The only way you can turn the lines on is do that, and then line 0 turns on, and then you can start sending data. But let's just reset everything real quick. So I think that pretty much explains the architecture of this. So let's explain it again. So data flows, goes into the ALU and the RAM. Then when you say, oh, I want outputs from it, the ALU gives an output back to the main data line, which goes all the way along here, down here, all the way along this line, all the way around and back through the program counter. I know, people hate me for that. And back out here, where you can put it into, say, something else like the RAM. Then the RAM just gives outputs on the same bus, and it gives outputs here, puts it onto this bus, and it goes all the way around and back in again. And then you can put it into the ALU. So that's very simple. So now let's actually get onto the RAM command. So we've got up to the subtract command. So then you have the 2, 1, read and write. Now here's where things get pretty cool. So this is the RAM commands, and you have up to 4 different addressable RAM locations. 00 is of course RAM location 0, 01, 1, 10, 2, and 11 is free. And you can basically address these RAM cells. These RAM cells have a nibble each, so your total storage of the entire computer is a whole 2 bytes. Or if you really want to be clever, you could include these 1, 2, 3, 4, 5, 6, 7, 8 registers and these 4 registers. So that's 3 bytes and a half of... Actually, you have your program counters 4 bytes of storage, even though these wouldn't really be used as storage because they're not viable, but you could. So almost think of these as registers or a cache just for your program. And just because, yeah, that's basically what it is. That's what RAM is. It basically just stores temporary data. Then, yeah, that's pretty much those commands. So these are what you address to. Then you have your read and your write command. Whenever you specify read, you also have to specify the cell you want to read from. So if I want to read from cell 0, I just put a read command and leave these two blank because that's cell 0. If I wanted to read from cell 2, for instance, I'd put the read command and also the cell 2 command. However, say I wanted to write, I would have to put the write command and one of the cells, and that would basically write it. So at the moment we've got this timing pretty much perfect. I mean, you can adjust it if you want. And that basically should mean you'd be able to write the number 1111 to cell 4 and it wouldn't break at all. But if you want to make it faster, of course, faster writing, then you could maybe potentially slow this down a bit. I'm not sure how viable it would be. So now, taking all these commands, we can use them together to make a program. So say I wanted to, let's do two programs. The first one we're going to do a simple adding program, and then the second one we're going to do the Fibonacci sequence. So as you can see, I already got the Fibonacci sequence programmed, but we're going to destroy this for now because I want to go through step by step, well, line by line, to be honest, with you guys, just to make sure you fully understand it and you know how it works, because it's always good to understand the programs. So I better actually explain what the Fibonacci sequence is, but I think I'll do that when we get onto it. It's basically like a nice simple program or formula that you can use on a computer, you can do in real life. It's a pretty cool thing. I don't really know what it is, to be honest. It's just a sequence. And algebraic sequence, not even algebraic, I don't know what I'm saying. So the number, basically what we're going to do is a simple adding program. We're going to add the number 2 and 5 and it should equal 7. However, we're going to want to do that. So on line 0, we're going to want to put the number 2 into register A, because we're going to want to do 2 plus 7. So that's as simple as putting the number 2 into ALU register A. Then on line 2, we're going to want to put the number 5, which is 4 and 1, into the register B. And then that's pretty much it. That's the entire program. And then say we want to also display it, don't we? Because that would be nice. Actually, we'll display each line. Where's the display command? So we're going to do 2 plus 5. Oh, no, we forgot the answer command. Now we're going to also want to display the answer, aren't we? And we're going to be doing add, so we're going to put add on that line. We're basically going to add those two numbers and also display the answer. Then we're going to want to come over to the actual program counter and do the workings out. So line 0, we want to execute it, then jump onto line 1 because that's the next program. So we'll just put 1 in. Then on line 1 we want to execute it and then jump to line 2, so we'll put line 2 in. On line 2, however, it's the end of the program. If we just leave it blank, it'll jump back to line 0 and loop. So what we do, we put line 2 on the line 2, which means it will stay on that line forever until you turn the computer off and reset it. So that should do the simple program. My advice is, when you make a program, set the clock speed to the max, see if it works, and then slowly change your clock speed and make it slower. But as I know this is a very simple program, I can set it to the max clock speed. Basically, to work this computer, we're going to have to reset everything. To reset everything, we clear all RAM. Well, first of all, we're going to make sure the computer's off and the clock is off. The clock is off when it's down. We want to reset ALU registers, clear all RAM, and update display. These three can be done in any order. However, the thing we need to do next is then we need... Actually, no. The first thing we need to do is clock it once. then we click these three buttons. We have to clock it once first, or it might not work. Then once we've done that, we can turn the computer on. So if I turn it on, it should execute the first line of code and put the number 2 into the display, as well as register A, which is this one. So 1, 1, 2, 2, 4, 4, 8, and 8. So 1A, 1B, 2A, 2B, etc. And as we can see, it has done that perfectly. It should also be outputting 2, because that's what the adder does, but it won't be giving a proper output yet because we haven't said add. Then the next line of code, we're going to clock it once. I'm not going to turn on the clock because this will be simpler. We're going to clock it once, and it should put that number onto display, and also the number 5 onto the display, and as well as the ALU. And as you can see, it has put the number 7 into B. So that's 1 on B, as well as 4 on B, and that is 5 in total. So I did mean 5. However, it has not put the number 5 onto display, even though we said that. That is because we have done our timings wrong. The way we would do that, if we actually wanted it to display, what we'd have to do is put a bit of delay between the display command. So it would have time to travel from the main data bus all the way into the display and then update. So that is a small convenience, minor inconvenience. That, well, I guess we might as well fix. So the way we're going to do that is we're just going to turn this one onto 4 ticks, turn this one onto 4 ticks as well, and then put another one on 4 ticks. And that should pretty much do it. I don't think we need it any slower than that. And then we clock it again. It should display the number 7 because it does thingy plus thingy. And I saw these update, but it didn't update in time. That is because we may need a few more repeaters. So if I go over to the right command over here and count how many repeaters I have 1, 2, 3, 4, 5 repeaters. Just to make sure the display isn't broken, I can just update it manually, and it should update to 7. Excuse me. Okay, maybe I have to do that, and then it should update to 7. As you can see, it isn't broken. It's just that these are too short. So what we're going to do is add 2 more and put them on forward. The only other thing I want to do is actually move this to here, just so we can use that update command while the thing's on. That is as simple as doing this and moving this to here instead. And that will make sure this one and this one will not interfere with each other, because if I hang on, they might actually do that. Oh well, I guess it doesn't matter too much. So now let's restart this. So if we make sure we turn it off and the clock is off, then we can just reset everything and it should update to 0. And then we clock it once just to make sure it goes back to line 0. And as you can see, the ALU is reset. Now we're going to try it again. We're going to turn the computer on, and it should immediately put the number 2 into the display. As we can see, it did that down there. Now we're going to clock it again. Now it should put that number in. Oh, I think I know why it doesn't change. That is because we're doing this on continuous lines, and it doesn't change, it doesn't turn it off for an instance. Okay, that is a small bug on my behalf, and I'm not particularly sure it's easily fixable. I guess what we could do is have an AND gate over here, and then yes, if we have an AND gate over here between this and this, which means it will update as long as it clocks as well as... Okay, that's very simple. So what we're going to do is over here, because this is probably the best place to do it, we're going to come out like this. And then over here, we're going to just break these for now. And we're going to make a very simple NOT gate like this. So this line goes into this torch, and this line will go into this torch. And this might actually need to be knotted. So what we're going to do is just this. It's not the most efficient thing, but it'll work. Then we're going to place a block like this, break these, place a torch like that, and there we go, it should go in. So now, and I'm just going to break these. So now what will happen is it will only update the display as long as it clocks and the display is going into it. So let's try this again. So if I just turn the computer off, then reset everything, then we're going to turn it on, and we're going to, oh yes, when you turn it on it doesn't automatically clock it. So if we clock it now, it should have sent a pulse. But that's another bug, isn't it? Because it misses out the first number, doesn't it? Don't know why that displayed the number 1. Maybe it was too slow. Aha. It seems this was a bit too slow for it. Or maybe this was a bit too slow. You might either need a pulse lengthener, or you know what, I mean, it really doesn't matter. We're just going to break this, because to be perfectly honest, you're not going to display on every line. And if you want it to do that, then you're going to have to jump between lines. So let's not bother about that bug. It's just going to be too annoying to fix. Maybe on a later video I might fix that bug, who knows. But yeah, that's our basic add program that unfortunately didn't work properly. But let's just try it out just one more time, just to see if it actually does the number 7. So what we're going to do down over by the display command is we're going to break the first 2, so it only displays the last number when it's finished, and we can read off of this small display over here. So let's just reset everything again. So now we turn the computer on, should have the number 2 into the ALU A, which it has. Now we clock it once, should put the number 5 into B, which it has. And if we clock it again, you should display the number 7. Eventually. I forgot the repeater. My bad. Now it should display the number 7. Perfect. Okay, let's just look how that did it. So it added these 2 numbers with the ALU, and as you can see, it has let the result of the addition, which is 7, because 2 plus 5 is 7, come out onto the main data bus, travels along the main data bus, and goes through it all the way down here. It's a very long time. Goes up here, all the way over here, and into the actual display. So that's how it basically works. Now let's actually try a more complicated program. So I'm just going to have a break real quick and I'll be back. So I am now back from my break, the power of editing, and we're going to be building the Fibonacci sequence now. So the way we're going to do this is, first of all, we're just going to break our previous program because we do not want it anymore. So problem about this computer is that it is ROM programming, which means you cannot store your program. Like if you wanted to program a different one on, you'd have to break your previous program and do it on another thing. The way you could fix this is either use RAM as the actual programming, but that would be a very technical thing, or just write it down in like have a nice layout in an Excel document where you have the ones and zeros all stored out, and you just write your program down in machine code. So over here is my version of a computer that can actually store the program, and as you can see, it is absolutely massive. Like, I mean, this computer is so big, I'm not sure if it would all render in properly. I mean, like, simulate with the simulation distance. But as you can see, over here we can program it with serial data input. It has a serial I/O, and you can program it with this, which is pretty cool. So you only use one redstone line and you can program an entire computer this big, you know. And over here we have the inputs. It isn't finished yet, and I'm not sure if I'll ever finish it, but it's a pretty cool computer. I mean, you can program it right now, basically. You can, what you do, you best specify the line you want to put in, and you can either select from this controller or the I/O, and then you put in your program with these levers, and then you specify the line and you hit send. And I mean, I can give you a demonstration. Let's just put these 4 on, and we're going to send it to line 2, and if we hit send, should send it. And as you can see, there's a program counter here. It was going to be a great computer, but I mean, I never got around to finishing it because I had other things to do, and I just wanted to do a different computer. So as we could see on line 2, I think this is line 2, we have those 4 things, and the program counter would basically just read from these RAM cells. Someone wanted me to do a tutorial on these RAM cells, and I might actually consider doing that because they're nice and only 2 wide. However, my friend Ducks and Plays actually made a very more compact version. Even though it was slower, it was a lot more compact, and with a computer this big, sometimes it's better for it to be slower than bigger, you know, because this only has 16 lines of code and it's absolutely massive. There's really no point. And I have come up with other RAM cells as well. The reason I used these was because they were I just made it really quick. They are fast and they're 2 wide tileable, which means you get a very nice way of doing it. However, if we look, I'm not even sure if I have any good RAM demonstrations. I mean, this will do. This is literally the exact same thing. As you can see, it's much more small. You have one cell, 2 cell, 3 cell, 4 cell, 5 cell, 6 cell, 7 cell, 8 cell. That's 8 cells, so basically double this would be like half of that, and it would store the exact same information. So as you can see, the only difference is this is 2 wide, which can be a bit annoying for some people. But yeah, that's basically it. And this is the RAM cell, which uses D flip-flops and D flip-flops and a bit of stuff to control it. And I'll probably do a video dedicated to that and some other types of RAM that I've come up with. Like, over here I was working on 2 wide tileable dual read RAM, but it didn't work because of certain complications. It looks pretty cool. It would technically be 3 wide tileable, which is actually pretty cool. However, it would not be 2 wide tileable, which is what I wanted, because these lines intersect. Say if I was to build another one, it would be like this. As you can see, these lines intersect and there would be no way to actually stop them from doing that. As you can see, I do have a dual read RAM design, which is this. You have your read 0 and read 1, as well as your write. This line is your read 1 and read 0, and this line is your write. So we better actually get back to the tutorial, because this is becoming a rather long episode. So I have the Fibonacci sequence program in front of me, and we're going to run through this line by line. So you should have destroyed your program, and we're actually going to start program this. So on line 0, we're going to input the number 1 to ALUB. The way we program that is we're going to go all the way to ALUB, and we're going to place a redstone torch on that line, and we're going to go to our main data bus, which are these 4, and we're going to put the number 1. So that is literally the entirety of line 1. The only other thing is we want to jump to line 2, don't we? No, I mean line 0. This was line 0. That's the entirety of line 0. The only thing we want to do is jump to line 1. So what we're going to do, come down to a program counter, put the number 1. Pretty simple. Now we've gone on to this line. On this line, we want to save the number 1 to RAM 1. The way we're going to do this is we're going to do write. We're going to put the write command in, and we're going to write it to RAM cell 1. You could write it to any RAM cell, but RAM cell 1 is faster. However, in fact, we can actually write it to RAM cell 0, because that is the very fastest it can go. So if we just leave it blank, it'll write to RAM cell 0. That may sound confusing, but basically it will always address whenever you put a thing in. So if you leave it blank, it will address to RAM 0, just because you put the command in. So that's basically that. Then we're also going to want to say, go to line 2, and we're just going to put a redstone torch like that. Then on line 2, we want to read that RAM 0, so we're going to put the read command in on line 2, and we're going to read 0, so we don't have to specify it, because it is being specified. And we're also going to input it to ALUA, as well as displaying it. So if you've got that down, that's pretty simple. Then we're going to want to jump to line 3. The way we do that is just put 3 in binary. Now on line 3, we're going to want to add both the registers. So we're going to find the add command, which is over here. We're going to add register A and B, and then we want to, what we want to do with that add data, we're going to want to save it to RAM 0. So what we're going to do is we're going to put the write command in, and we're going to write it to RAM 0. Pretty simple. Then we're going to want to jump onto the next line, which is line 4. So the way we do that, put 4 in binary. Now on line 4, we want to read RAM 1. So we're going to go all the way over to our RAM, and we're going to input read. So we're going to want to read RAM 0 actually, because we're doing on line 0, I mean RAM 0. We're also going to want to display it. So where's my display? It's over here. As well as inputting it to ALUA. Pretty simple. Now here's our last line. We want to jump from line 4 to line 5. So that's on this line. And on line 5, we want to add the register A and B again, as well as saving it. So we're going to write to RAM 0. As you can see, there's a sort of pattern in here. And then the last thing we want to do is jump back to line 2. So 0, 1, 2, which is this line, and it will repeat these 4 instructions over and over again until it overflows. And I'll show you what I mean by overflows. So we're going to want to specify the line 2. So now that we've done that, what we're going to want to do is come over to our user interface, and we're going to reset everything and make sure the computer's off, of course. And of course we have to clock it as well and stuff. Now we're going to want to test this program. The way we can test it, there are 2 ways to run a program. You're either going to test it, or you're going to actually run it. Running it, you turn the clock on. Testing it, you clock it manually, check everything and make sure it's executed those lines. So we're going to clock it manually, and then we'll use the actual clock. And of course, when you're using the actual clock, I'll come to that in a minute, you'll have to do stuff with the repeaters. So as soon as we turn it on, it should execute line 0, which line 0 was input the number 1, which is over here, to ALUB, right? So if we go over here, it has inputted the number 1 to ALUB. Very simple, and it has done what it's said. Then, as soon as this clock cycle finishes, it says jump to line 1, which is this line. So on the next clock cycle, it should jump to line 1. So if you clock it once, it's a jump to line 1, which it has over here, from line 0 to line 1. Now, on line 1, we said save the number 1 to RAM 1. So if we go over to here, or RAM 0 even, we said save the number 1, which we did not do, apparently. So that's why you always have to check your program, and why you have to do it. So if you put a redstone torch on the RAM. So let's just reset it again, because we clearly, well, I clearly did the programming wrong. So if we just reset it all, then turn the computer back on, should execute that line, and should save 1 to register 1, which has not done yet. It should have. Oh yeah, we forgot to clock it. That is why whenever you turn the computer off, you always have to make sure you hit the clock once button, just to reset the registers down here to 0. As you can see, they've reset to 0. And that's very important. So now if we turn the computer on, it should execute that first line of code and put it into ALUB, put the number 1 into ALUB. Now if we clock it, we should jump to line 1, which it has, and put the number 1 into register, well, RAM 0, which it has. Perfect, because this is RAM 0, RAM 1, RAM 2, RAM 3. And RAM 3 is always going to be the slowest because it's the furthest away, and RAM 1 is always going to be the fastest. So, I mean, they should all be the same speed, but take that in mind. It's only like 1 or 2 ticks delay, but just because it's a redstone computer, it's Minecraft, you have to have repeaters to extend the signal length. There will be a bit of delay in the RAM, meaning the RAM 0 is always the fastest. So always use this RAM 0. So you can almost call this a cache. This would be your L1 cache, your L2 cache, your L3 cache, your L4 cache. The L1 cache is always the fastest kind of thing, and will always have the information most applicable to the situation. So that is, yeah, that's pretty much what describes it. So now it has saved the number 1 to RAM 1. Now we're going to go on to line 2. It should read RAM 1, display it, as well as input to ALUA. So if we clock it, it should go on to line 2, which it has. It should display the number 1. Or, well, actually no, it should read the RAM 1, or well, RAM 0 even, which it has. Display this number, which it clearly has because the number in the RAM was 1, and it has displayed it. Perfect. So now we're going to go on to line 3, which is add that number over there, as well as save it to RAM 0, which this command actually relies on repeaters, timings. You would normally have to do another command in between this, but you can do this because it relies on repeaters and it's quite clever. So I think I've read that right. So it should, actually no, it should, oh no, I've gone wrong, I was correct. So when you add, it basically adds these two registers, so it adds 1 and 0, then saves it to that RAM, so the RAM that's actually displaying it gets saved with the new data. However, the display will remain the same, even though that data will be changed because it's got registers. So if we clock it, it should add these two numbers. As we can see, it adds them, and it should put them into register 1, which it has, because 1 plus 0 is 1. Now, it should remain 1 on this display, even if we change it to something else, because we haven't updated it yet. Now, however, we want to go into line 4, and it says read RAM 0, display it, and also input to register B. So if we clock it, I missed the clock button, it should read that, which it has, display it, which it has, it's displayed the number 1, and also input it to register B, as it has. Now here comes the looping part, you'll see. So on line 5, it adds those two numbers, so 1 plus 1, and then also saves it back to RAM 0. So we clock it again. Should add these two numbers, it should go into the next cycle, add them. So you can see it's now 2, and it should also save it to this RAM. As you can see, it does, and it's saved it. Just a side note, you can't get numbers out from the ALU as well as numbers from the RAM, or the data will corrupt. I mean, you should know that because it's a single bus data line. So now, that's the last line of code, isn't it? Now from this line, it should go all the way back to line 2. And on line 2, we said read the RAM we've just saved. So it'll read the number 2, display it, so it should display it, and also input it to ALU A. So now the ALU will have the number 1 on ALU B and the number 2 on ALU B, then it'll add them on 3, then you get the number 3, you repeat the whole program, plug the number 3 in, and then you do 3 plus 2 is 5, then the number 5 goes in, then 5 plus 3 is 8, then it goes in again, 8 plus 5 is 13, then it goes in again, and then 13 plus 8, but that's over 15, which is the maximum of this 4 bits, and it will overflow and it will break. And there's no breaking indicator, it just overflows. What if you really wanted to do, you could have an overflow indicator by basically taking this over here. Actually no, this is on subtract. You'd have to do it on add because there's no overflow on subtract. You'd basically take this over here and put a small indicator, like, I mean, you could have a light over here, and this light will basically go over here. So whenever it overflows, that light will turn on saying, oh, it's overflowed, do something. But this computer's kind of dumb because we don't have conditional branching, so it will not know it has overflowed, which does not matter. So if we clock it again, it should display the number 2 eventually, as we can see, and we can just keep clocking it, and every 2 clock cycles it will display a new number. And if you've done this computer the exact same as I have, where you've put all the repeaters with the exact same timings that I have in the exact same place, then I can show you how to clock it. So that, I think I clocked it too fast. So we're just going to turn this off, reset everything, just to make sure. So now, how do you clock a computer? Clocking it, well, you clock it by giving it a clock. How do you adjust a computer's clock so it hits this button automatically? Because you don't want to do that, you want the computer to automatically do that. How do you do that? Well, you go over to the clock, which is over here, and this basically is a clock, and each amount of time it shows, every single time it will give a pulse and update it to the next line. So say you wanted a clock speed of 5, so every 5 seconds it would do that. You'd have to set this to 5. Your clock would be 5 seconds long, and on that 5th second it would pulse and update it. So the way we're going to clock this program is, of course, we have to go to the maximum setting possible, because we don't know how long this program might take, because different programs take different clock settings, or like different programs take different clock speeds, is what I meant to say. That's why clock speed doesn't always matter on computers. Everyone's like, oh, I got 2.5 thousand gigahertz on my computer. That does not matter. Sometimes it might be trash, sometimes it might be amazing. Normally higher clock speeds mean faster computer, but that doesn't always apply. It also applies to how well the computer's made, the architecture, how fast it is, how optimized it is, and a lot of other features. So the way we're going to do this to clock it is we're going to set it to maximum clock cycle, test the program. I already know the clock speed for this program, so I'm not going to test it. And if it works, decrease it a bit. If you can decrease it a lot. If it breaks, then increase it a bit. But basically you have to keep decreasing and increasing until it is exactly spot on and it is fast as it can go. That is basically how you adjust the clock for your program. And different programs, as I've said, will have different clock speeds. You want it as fast as possible because you want the computer to run as fast as possible, don't you? And if you wanted to run as slow as possible, you can always change that to very slow. But I'm not sure why you want the computer to run slow unless you're debugging it, where if you're debugging it, you just use the clock once button. That's why this button is so useful. So I already know the clock speed for this program because I've already been adjusting the clock to save some time. So basically, it's maximum clock speed. So 1 tick, 2 tick, 3 tick, 4 tick, 5 tick, 6 tick, 7 tick, time 2, 14 ticks. The clock speed of this program is 14 ticks, which is 1.4 seconds. So every 1.4 seconds, this clock will execute a line of code. That sounds pretty fast, and for this computer, it is very fast. This is a very fast 4-bit computer. That is a very fast figure, and you can say, my Redstone computer only executes a line every 1.4 seconds. That's 1 hertz is 1 second, right? So 1.4 seconds would be, I don't have a calculator, I think it's like 1 divided by 1.4. Let's just grab a calculator real quick. We could calculate it on this computer, but I'm not going to be bothered. 1 divided by 1.4, it's a stunning 0.714285714287 reoccurring, by the way, hertz. So 0.71 hertz, that's, I mean, it's very fast for a computer of this size. And I mean, computers, Redstone computers, I doubt for a very big one are never going to really go over 1 hertz. They're always going to be under 1 hertz normally, unless you've got it really optimized and made to be fast. Then it's a normal Redstone computer wouldn't really be super fast. However, this one is going to be rapid. So let's actually try our program out with the clock speed of 1.4 seconds. And I know I've said 1.4 seconds here, that's per line. However, the display will update every 2.8 seconds because it takes 2 lines to calculate the next number. It doesn't take 1 line, it takes 2 lines because of the way the actual program works. So it should it will execute a line of the program every 1.4 seconds, but you'll only see results every 2.8 seconds, and it will be delayed, of course, because the display is delayed. So let's turn this on. So make sure you reset everything by clocking it once, updating everything, and resetting everything. I mean, you could have one big button that does it all if you really wanted to. There are lots of ways you can customize this, and without further ado, turn the computer on. Whoa, didn't that feel good? Now we're just going to turn, it should have done the first line, as we can see it did. And you know what, I'm not going to show anything else, we're actually just going to show the computer in action. So if I just hit the lever on, it should slowly go. So the sequence goes 0, 1, 1, 2, 3, 5, 8. You know, it's already done 0. Now it's done another one. Now it's done 2. Should do 3 next. 5. Don't know why that broke. It's probably an error. 5. 6. Okay, we've clearly done something wrong in the programming. That's just adding 1, isn't it? I think maybe I have to remove this torch. So the 1 on the second line you're going to have to remove. I don't know why that was doing it. Let's try it again. So if we turn the clock off, turn the computer off, reset everything. That's quite embarrassing. I do not know why it did that. Let's just try it again. So it should take some time, but it should eventually. 1, 1, 2, 3, yes, 4, not 4, I said 5, I meant 5. Okay, I don't know why it's adding 1. Yeah, I've probably done something wrong in the programming. This was working earlier. So what we're going to do to fix this is we're just going to slow it down and see if it works. and then I'm going to have a break and then check out what I've done wrong. So if I just try it again, there's probably something that I've done wrong. I mean, I'll figure it out eventually. It just may take some time. I've just thought of what could be going wrong. It might be this is too slow. It should go to 3, now it should go to 5. The number 4 is going down. Yes, so we've created a +1 program. That is not great. I'm going to have a little break and actually see what's wrong with the programming. Then I'll come back to you, because there is definitely something wrong. This is very embarrassing, but I'll find it eventually. So, I found the mistake. It was a very simple mistake. A very stupid mistake. Let's just reset everything, and I will show you where I made the mistake. So, first mistake, that torch, the 1, is actually meant to go on that line. So I broke this torch, place it back, put the torch on line 1. So put the line 1 on line 1. You do not need it, but to make the program faster, it is preferable that you would have it. So now, the second mistake, the big mistake, on line 4, I said input to ALU B. However, I had placed the torch on ALU A. Yeah, that did not work, I think. Yeah, it didn't work on ALU A because it wouldn't be inputting any number to ALU B. So, what I had to do is your torch, it would look like this on your screen on line 4. So 0, 1, 2, 3, 4. Line 4, it would look like this on your screen. Break this torch, put it here on ALUB instead. That was a very stupid mistake on my part, and I don't know how that skimmed over my head. So let's actually try this again. So first of all, we're going to clock it once and make sure everything is cleared. Then turn the computer on and let's see if it actually works. So the first number should be 0, then 1, as you can see. Then it should go 1 again. Then it should go 2. Then it should go 2 plus 1 is 3. 3 plus 2 is 5. Perfect. 5 plus 3 is 8. Perfect. 8 plus, I don't even know, 5 is 13. 13 plus 8 overflows. As you can see, it's already overflowed. Like if we went over here, it would have overflowed. As you can see, it's overflowed, which means it's broken, and it's flashing now because it's broken. But as you can see, it actually works, which is very impressive. So I really hope you enjoyed building this computer, and I hope it gives you a lot more inspiration and stuff to join the Redstone engineering community and actually do something just cool, I guess. I mean, it doesn't need to be, it can be a hobby, you can just do it in your free time. I mean, it could just be because you're trying to learn a bit of computing, and this would have helped you make a proper computer in the real world. Who knows? I hope you actually learnt a lot from this. I may be doing a few more videos of this actual computer doing like bug fixes and stuff. But as usual, this is the last part, so any questions I will try to answer in the comment section. However, please remember that YouTube doesn't always give me notifications, so it might take a few months before I respond sometimes, because YouTube's rubbish with notifications. But I really hope you enjoyed building this computer, and I actually hope you learnt a lot about how computers, well, Redstone computers work in general, and normal computers, but Redstone computers mainly. So I hope you actually saw something of this computer that you liked, like maybe you liked the style of user interface with this. I originally got this style of user interface from the computer Bluestone, where it has a nice adjustable clock out front. it's an amazing, stupidly compact computer, so I would definitely check it out, even though the creator has long ceased to exist, apparently, as with many creators, which is pretty sad, as the only big content creator for Redstone engineering nowadays, on this current date is of this video being published, is Nubosaurus, and he's pretty good at his stuff, but he doesn't upload regular. Well, I can't even say it. He doesn't upload that much, which is quite sad. So, but he has a lot of stuff to do, as with most people who do these. So, I hope you learned something. But yeah, because that was kind of. So, as you may have noticed, my recording cut out. That is because I have 2 megabytes on my disk left. So, wrong. Yeah, I was recording to the wrong hard drive and it cut out. Basically, what I was saying, I went and I didn't even realise it cut out. I did a whole load more stuff that I was talking about, what I was going to do and stuff. Basically, I hoped you learnt a lot of stuff from this. I hoped you learnt some components that you could have done. It's quite easy to upgrade. If you wanted to upgrade this, why not make it an 8-bit computer instead? That's what I did over here. This is an 8-bit computer based on the same thing. The same architecture. It's literally the same layout, just a bit different. Well, not really that different. And as you can see, it's 8 bits. And it's lacking a lot of stuff, but it works and it's pretty cool. So I did hope you learned something, and I guess, yeah, this has gone on far too long. So I hope you like your Redstone computer, because if you've built this, I know it takes a long time to build. I've been building on tutorial, and I would say it's taken me in total around, I don't know, like 8 hours to build the whole thing on tutorial on a video. But yeah, it's probably taken you longer, because I know tutorials are always kind of hard to follow. I've done everything on camera as much as possible, so you should be able to easily follow it, hopefully, I guess, as long as I'm not moving my camera around too much. But then you get motion sickness, you know. But yeah, I hope you're happy with this Redstone computer. If there's something not working, try and comment, see what's not working, try bug fix. Even if it's just one piece of Redstone broken, try check everything, just make sure you can fix that one piece, because that one piece could potentially break your computer. So the best way to test it is just test out each individual part. So test out all the RAM cells, test out all the different types of ALU operations, test out the display, each and every number, put it in, see which part's broken, isolate the point where it's broken, try and fix it. This computer should work in future versions unless there's a big change in Redstone, which I do not think. So currently working 1.16, and it should work for older versions as well. And yes, I guess, yeah, it should work in the future, hopefully. There may be, as long as Bedrock Edition doesn't update pistons to have quasi connectivity, or like Java Edition. That would be sad, but I mean, I doubt they would. So yeah, hope you like your computer, hope it worked. You should be able to write some pretty cool things for it, maybe upgrade it a bit. But yeah, in general, I just hoped you actually learned something from these videos. So yeah, I guess it's gone on far too long, as I've said already. Please like and subscribe, and I am out. Also, new outro, by the way. See you later.